Hello and welcome to part 3 of my Code It Yourself sound synthesizer series. The music you can hear playing in the background is the Marble Machine by Wintergarten, synthesized by the sound synthesizer that we've made. And not only is it a wonderful melody, but it highlights the 3 things that we're going to talk about in this video. The first is looking at frequency modulation, which is very important for giving a real texture to the sound. This is ever so subtly changing the frequency of a note whilst it's playing. For the second part, we'll be looking at voices and instruments. Can we come up with a nice data structure that wraps up everything that we've done so far, so the oscillators and the envelopes, to represent a particular instrument? And finally, at long last, we'll be looking at polyphony, or polyphony, depending on where you're from. And this is the ability to play multiple notes at the same time. Let's get stuck in. I'm starting with the code that we used at the end of the last video. And if you remember, this code really just contains a simple oscillator and an envelope. And all of the good stuff happens in this make noise function here. Let's have a listen so far. Very nice, so we can hear the envelope there and we can hear a sawtooth wave. We're going to be looking at frequency modulation first. It can be quite complicated. There is a significant amount of maths behind the theory of frequency modulation. I'm not going to go into the full derivation of the formula. It's not really the scope of this video, but we'll take one that's ready-made and I'll try and explain bits of it. The purpose of frequency modulation, though, is to add a little bit of vibrato to the sound. And this can add a lot of depth and character and texture to the tones that we can hear. Whereas I would usually talk through the theory and then write the code, I'm going to do it the other way around this time so we can listen to the effect first. That might make explaining the maths a little simpler. So I'm going to make some modifications to our oscillator function. For now, I'm just going to hard code in the frequency modulation code. The code here will take a low frequency 1 Hz wave to modulate the note that I'm playing. And what we should hear is a siren-like sound. We do, and if I choose a different note, the overall pitch of the siren is a different frequency. If I increase the frequency of our bass signal here, we can see it's twice as quick now. And now it's less harsh. That's because I've reduced the amplitude. Sirens aren't typically considered an instrument, so let's try and make it sound a little nicer. The effect of frequency modulation is very subtle, so I want the amplitude to be quite low, and I'm going to change the frequency to about 5. Let's have a listen. So you can definitely hear that vibrato effect. It's quite nice. Here I have 2 sine waves. The blue one at the top will be our note, so this is typically a high frequency. You can see I can change the frequency on the slider here. And the sine wave at the bottom is our low frequency. This is, in frequency modulation parlance, the top one is called our carrier frequency, and the bottom one is our message. Up here I've entered the formula for frequency modulation. Let's enable it and see what the waveform looks like. And we can see when the 2 waveforms are modulated, we see a clustering of low frequencies followed by high frequencies, and low frequencies and high frequencies. And so if I very gently change the low frequency, we can see the clusters get tighter and tighter. And if I change the higher frequency, which will be the note, we can see that also changes the output waveform. We can change the effect that the low frequency has on the high frequency by altering its amplitude. And I call this a fudge factor, but this is actually quite a complex phenomena in the frequency modulation equation. So if I reduce the amplitude, we can see we've just left with the original note, and as I increase this value, we see that the frequency modulation becomes more prominent. And you can do interesting things with this. In fact, if I turn it right up, we start getting very interesting waveforms indeed. Now don't discount these straight away, they might actually sound fantastic. Let's go back to our very first oscillator equation. And let's consider the low frequency oscillator part first. So we would have low frequency oscillator's amplitude, sine of the frequency that we want, times t. Now, if you remember from our earlier videos, when you want to mix frequencies together, you add them. So we also need the frequency of our note, times t, and we add them together. And that gives us our overall frequency, which then we can pass into another sine equation to give us our output result. Now the keen mathematicians out there may have spotted something a bit odd about that and the use of t. I don't want this to be a video about mathematics. And if you're really interested, there are many resources online that talk about how frequency modulation is really a combination of trigonometric identities and calculus. Suffice to say, the equation we're left with at the end is a bit of a bodgy approximation, but it's good enough for the purposes of this video. I'm now going to modify our oscillator function so it always uses a low frequency oscillator. So I've included here the frequency and the amplitude, but I'm giving them default values in case we don't want to use it. And I'm going to create a base frequency so we can use this frequency in the other types of oscillators. This was our amplitude. And so our sine wave simply becomes the sine of the frequency. Now the only one that's tricky to modify here is the digital approximation to a saw wave, because it doesn't use d frequency. And it works in real time and doesn't use angular velocity. That said, the translation from hertz in real time to angular velocity is trivial. I'll leave that as an exercise for you. And I prefer the analog sawtooth wave anyway. So here's our original oscillator function, and we'll just play it, make sure it still works. Nice, very smooth sine waves, but now we've got some additional arguments we can pass in. So the first thing is our frequency, so let's set that to 5 Hz, and we'll set our amplitude to be quite small. Maybe too small, let's try that. And just for kicks, let's see what the square wave sounds like. I like that. Now that we've got envelopes, oscillators, low frequency oscillators and frequency modulation, we can have a crack at trying to create realistic sounding instruments. Let's have a go. I'm going to try and make a harmonica type sound, like you heard at the start of this video in the audio track by Wintergarten. I know a harmonica is a reed instrument, and it's a breathy reed instrument, so for reed you typically want square waves, and for breathy sounds you want noise. Now remember, for noise oscillators it doesn't matter what the frequency is going to be. So I'm just going to put 0. D time, pass that in. And the type is oscillator of noise. Let's have a listen. Well, that doesn't sound anything like a harmonica. Oops, silly me. There we go. Don't want to add in just a load of noise and a DC offset into the signal. It's better. I've added another note, so it's actually playing a triad of notes now. It does almost sound like a harmonica. If we listen ever so carefully, you can just about hear the low frequency oscillator working there. Let's just duplicate all of this for the moment and comment out this so we can store this setting for later. So we know that this is our harmonica. And now let's make a glockenspiel, a bell type sound. So I'm going to, instead of using square waves, I'm going to use sine waves. I'm going to keep the low frequency oscillator just the same. And I'm going to use the second and third harmonics of the original frequency. 2 and 3. And we don't want any noise with the bell. It's a very crisp and clean instrument. Let's have a listen. And we'll just change these square waves to sine waves. Well, that doesn't sound anything like a bell. You can see it's a bit hit and miss, this instrument creation. The problem we have here is our envelope is completely unsuitable for that of a bell. We want a very short attack time. And we want a definite decay time. And bells can't sustain, so we have no sustain amplitude. And they release over a fixed time. Let's have a listen. It's not quite high enough frequency yet. Let's double all of these. It's a bit more bell-like. As you can see, it takes quite a bit of time to find an instrument, and I'm not very good at it. And so when I find one that actually sounds like an instrument, I want to record those settings. I think it's time we create a data structure that represents an instrument, or a voice. I'm going to create a base structure, simply called instrument. An instrument is defined by two things. First of all, its overall volume level. And secondly, the envelope. By including a virtual function for the actual synthesis part of the instrument structure, we can override this with base classes, or base structures in this case. And we'll make that pure. And of course it returns a double. We can now encapsulate the whole definition of an instrument in a base class, which inherits from instrument. So at the moment we're working with a bell. Let's keep our bell. And the first thing the bell should do is define what its envelope looks like. So we'll do some cut and paste. And now we'll override the sound function for the actual synthesis. And let's cut and paste the output. And we'll just tidy this up a little bit. And all this function needs to do is return the output at the time that it's been given. Now that we're working with instruments, we need to modify our program slightly. So I'm creating a pointer here to the instrument, which is the base class of instrument, so it can point to, of course, anything that inherits from the instrument base class. I'm going to change our make noise function. All we need to do now is call the sound function of the voice that we're using. And the next change to make is to create the voice. So we have our voice initially, it's null pointer, but we're going to change this into the bell sound that we've just defined. And of course we must also notify the voice's envelope that we've started a note here and that we've released a note here when the key is pressed and released. Let's have a listen. Now I'll wrap up our harmonica as well. So I've typed up now the harmonica, and to use it all I need to do is declare the voice as being a harmonica. Let's have a listen. Very good. Now that we've encapsulated an instrument, the only thing left for our synthesizer is polyphony, playing more than one note at the same time. If I play a note now, we can hear, sounds fine. But if I play two notes at the same time, it completely falls apart. I think we've outgrown the code here now, so I'm going to refine everything that we've done so far. Try and make it a bit more readable, a bit more usable if you guys want to use this code. And by making it more modular, we should be able to get polyphony up and running. Right, I've tidied up the code a little bit, and the first thing I've done is change the basic type from double to F type. It's still double for the most part, but it also allows us to use integers on other kinds of hardware. And I've created a namespace called synth. And what you'll see in this namespace is pretty much exactly what we've got already in our program. We've got our W function for doing angular velocity. This is a basic note structure. Instead of storing the frequency, I'm storing the ID of the key on the keyboard, and I keep track of the times when it was switched on and off. I also store something called the channel, and this is effectively the voice. You'll see the oscillator hasn't changed at all. And I've included a function called scale, which takes the note ID and translates it to a frequency. And this may look silly, but it's exactly the same as we had before. I've refined the envelope structure a little bit. It has exactly the same variables and operates in exactly the same way as before. But there were a few glitches, for example releasing the key whilst it was still in the attack phase. All of these bugs have been ironed out, but the principles are exactly the same as the first two videos. It's just tidier code. The only thing that's changed now about our instrument structure is the sound function takes the note instead of the frequency, and we use the scale to work out what the frequency should be. As you can see, the envelope uses the note on and note off, and we can pass back a boolean here when the amplitude goes below 0. We'll make a fairly crass assumption that that means the note has finished. Of course, not all instruments will have finished, but we'll assume if it's making no sound, then it's not going to make any further sound. Here's our harmonica as before. I'll come back to the make noise function in a minute, but we'll see that the main is pretty much the same as it was in the first two videos. So I've got the get async key state to get the keys that are being pressed, and that's it. Let's have a listen. Multiple notes being played at the same time. So how do we handle polyphony? There are two ways. One is we could have an oscillator for every note on the keyboard that's constantly outputting something, even if it's 0. Although this is very, very inefficient to do. The approach that I'm taking is that any note that is active, that is outputting its sound, has its own oscillator. So we're going to store all of the notes that are currently being pressed in a vector. Our make noise function will iterate through this vector and generate the frequencies and mix them together. When a note has finished being played, i.e. it is not outputting any more sound anymore, not necessarily when the key has been released, but when the synthesis outputs 0 amplitude, we'll remove that note from the vector. So this here is my vector of notes. And I'm going to be using two instruments. I'm just going to stick with the harmonica for this one, so we'll stick to a single channel. And now we'll look at the make noise function. Make noise is still the same as before. All it does is amplitude and output. But we need to handle a vector inside it. So I'm using some modern C here. We're going to iterate through the vector of notes, and we're going to play the correct instrument depending on what channel that note is using, and we'll mix the output. Simply mix them by adding them together. If the note has finished, then we want to set the note's activity flag to false. This will signal that it should be removed later on. In fact, it is removed from the vector using this lovely bit of code here, which is a lambda function. You'll have noticed at the start of this function, I'm using a mutex. This is to protect the vector of notes, because the sound machine, the background, the OLC noisemaker.h file, starts its own thread to handle the sound synthesis. And that thread is not synchronized with the main thread which handles the keyboard input. So let's have a look at how we're handling the keys. As before, we use getAsyncKeyState to determine which keys are being pressed. I then use the findIf function here on the vector. I search the vector of notes to see, does a key that has been pressed already exist in our vector? If no key has been found, as in no note has been found that's attributed to that key, could also interpret that as being the key simply hasn't been pressed, then we want to add it to the vector. So we create a new note. So here's the key has been pressed state. We'll create a new note. So we set the ID to what the key input is. We set the time that the note was started to now. We've chosen harmonica, which was channel 1, and we say the note is active. And we add the note then to the vector. If the note already exists in the vector and the key has been pressed, it's just being held down, so we don't need to do anything. And finally, if the key has been released and the note exists in the vector, we don't want to remove the note from the vector because we now need to let it do its release phase. So we set its time off to now, and we know that the make noise function will do the automatic removal from the vector later on. And that's all for Polyphony. I've tried to optimise the amount of computing resources attributed to generating the sound. And it's quite nice because now I don't have to be as precise when I'm pressing the keys. It allows for much more fluid play. I think the code-it-yourself synthesizer is now in an almost finished state. It's certainly usable by yourselves to generate all sorts of interesting sounds. The next video will be about sequencing these sounds automatically and interfacing to things like the MIDI protocol and other instruments. All of the source code for this project is available at GitHub. See the links below, and they're also on the onelonecoder.com blog. If you've enjoyed this coding video, please check out some of my others. I've coded all sorts of weird and wonderful things. And give me a thumbs up and subscribe, it does help. See you next time.